Is that a go?
Yes, you can. You can start now. It's live.
Okay. 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 Good evening, everyone. This is Blockgames live session. I'm Toby, and I'll be working with Oyin Damola. We're going to be talking about blockchains as a distributed ledger technology. We're going to be talking about nodes. We're going to be talking about transactions. Okay. So under distributed technology, ledger technologies, we're going to talk about like definition. We're going to explain how it works. I'm also going to give examples of distributed ledger technology. We're also going to look at blockchain as a distributed ledger technology. We're going to look at the immutability of blockchain, its fault tolerance, and peer-to-peer networking, and also understand the cryptographic back end behind blockchain technologies. Under nodes, we're going to look at types of nodes and like how to set up a node. Under blocks, we're going to look at the structure of a block, its creation and its verification. And we're going to talk about transactions, authorization, immutability, and the double spend problem. Okay. So in a distributed ledger technology is a protocol that enables the secure functioning of a decentralized digital database. What that basically means is that we have like a distributed database or distributed record of data across multiple systems, basically. So each system has a copy of that data. So in which a distributed database system is a computing environment in which various components are spread across multiple computers or other computing devices on a network. These devices split up the work, coordinating their efforts to complete the job more efficiently than if a single device had been responsible for the task. What that basically means is that when we have multiple computers contributing to a network, we basically have all of their resources contributing to that network. So we are able to achieve more because like the tasks are shared across multiple systems, basically. So a distributed ledger is an example of a distributed system because basically we have like a distributed database across multiple computers. So each computer has a copy of that database. So when the decentralized database is launched, basically each node has ability to access that database and its records basically and see changes that are made to that database. So you can access it from different geographies, from different institutions, and from different computers. That's the idea of distribution. It allows transactions to have public witness, which means that the public or any node is able to check the database and see when something happened, basically. So each participant at each node of the network can access the recording shared across that network and can own an identical copy of it. So distributed systems are not only limited to blockchain technology or Web3. It's actually a very old concept. So we have examples of distribution in maybe version control. An example of that is JIT. So each computer has a version of like changes to the repository, and each version system has a record of like logs basically. So each node is able to verify transactions. Though in the example of
So
version
please, can
control,
you slow down? Please, can you slow down? People are complaining. Please slow down.
okay, very sorry about that. Okay, so a distributed ledger is an example of a distributed system where a database is consensually shared and synchronized across multiple sites, institutions, or geographies accessible by multiple people. It allows transactions to have public witness, which is the ability for like anybody to go on the database basically and retrieve records and verify transactions basically. So the participant at each node of the network can access the recording shared across the network and can view its logs basically and can own an identical copy of it. So each system in the node, each network or each node in the network rather can have a copy of the records basically of each transaction in the ledger and can view and verify that. An example of a distributed system is JIT. So each computer has a record of the code base. Each computer can view like changes to that code base and can view the log of the code base. Distributed ledger technology is the practical implementation of a distributed ledger. It's the protocols and the systems that allow for recording transactions between multiple parties in multiple places at the same time. DLT deploys cryptography and consensus mechanisms to allow participants to share an immutable replica of the same ledger. So basically, everybody on the network has the same copy of the same data. So everybody can view the exact same copy of data. Everybody can access logs. Everybody can see when changes are made. It gets rid of the need for a central store of data and dispenses with the requirement for a central authority to carry out administrative functions like maybe ID verification or credential storage, maybe password management. Because in a decentralized network, we don't have need for a centralized server to manage these activities. Each node is capable of verifying transactions in a purely decentralized state. Okay. So here we have a diagram of a centralized and decentralized ledger. And we see that we have like a centralized system basically that serves each node or
Sorry,
each
Toby. Sorry,
client.
sorry to cut you short, but please increase the volume of your voice and please go slowly. People are complaining too much. I beg, I beg.
Okay.
They are saying you
Okay.
are playing at a speed of 0.75. Please.
Okay. So centralized ledger. Okay. So we have a diagram of a centralized ledger and a distributed ledger basically. So in a centralized ledger, we have like a single server that's catering to the services of multiple clients. So that server houses all the data. That server is going to handle all the requests. That server is going to like perform like auxiliary functions like maybe ID verification, KYC, that's not your customer. So that's what happens in a centralized system. If you look at the distributed ledger, we see that each client has a copy of the database, so there's no centralized system. So each copy can verify, each copy can also make their own transactions, basically. Okay, so how does the distributed ledger work? How does the distributed ledger technology work with the distributed ledger? Okay, a distributed ledger can be described as a ledger of any transactions or contracts maintained in decentralized form across different locations and people. The participant at each node of the network can access the recording shared across that network and can own an identical copy of it. Any changes or additions made to the ledger are reflected and copied to all participants in a matter of seconds or minutes. This eliminates the need for a central authority to verify transactions, and we can touch trade and exchange freely in a trustless society or network. So one of the problems we have when we're trading as of now in the current state of things is that we need to trust who we're dealing with. For example, if I'm to send a transaction to maybe somebody else and I want to send money, I would have to trust the bank to transfer that said amount to the other individual. I'm trusting the bank because there's actually no way for me to verify that the bank actually sent that money. So in a centralized environment, we're dealing with a trusted system, basically. So each client is trusting the server to do its obligations and to perform in a transparent and clean way. Obviously, that's not always the case. We have like frauds and Ponzi schemes out there. So that's why there's a need for like privacy and security and the need for like to develop systems that allow us to engage in like a trustless society. The most important elements in a DLT are cryptography, peer-to-peer networking, and game theory. Okay, so cryptography is used to verify transactions, to verify identities, to authorize. So, for example, your private key is used to authorize transactions from your wallet to any other wallet or to make payments, for example. We have peer-to-peer design, which is the idea that each node has access to that database and has a local copy of it. So every peer can network with another peer to maybe send transactions or to work with each other. Okay. Then we have game theory, which is the idea that we are applying gamification to the consensus process, basically. So there's mining going on, which is like rewarding miners for verification. So that's the idea behind game theory. So these ledgers tend to be write once, read many in nature because of the deterministic nature of the records and the system's mode of consensus. What that basically means is that it's relatively impossible to like make a change to a blockchain record because like it's immutable basically. Each party has agreed on its veracity basically and have added it to the record. So to change that would mean to change the history of all blocks that were built on top of that particular block. So it's relatively impossible to do that. So it's more of a write much and read many, write once. So you can't really modify data in a blockchain. And because of the nature of the mode of consensus, for example, we have miners going out like trying to hash multiple transactions together. Any single change to those transactions is going to cause like the hash to change, which will make the whole blockchain invalid at the end of the day. So that's why we have like oracles when we're trying to pull data from external data feeds, basically. So when we're talking about distributed systems, we're going to have to talk about the CAP theorem. Okay, so the CAP theorem is a way of describing like how distributed systems work, basically how IT systems work in general, and like describing their faults and their strengths. So CAP stands for consistency, availability, and partition tolerance. Okay, so CAP demonstrates how strong an IT system is and is particularly applicable to distributed ledger technology. For a distributed system, it is theoretically impossible to simultaneously provide more than two CAP properties. A distributed system is either always available and insensitive to network failure of the distributed system, but then you cannot guarantee consistent data. What that basically means is in the idea that like a node goes down or a node is not able to communicate new transactions to the general pool of nodes, there's always going to the data is always going to be available from at least one node, and the network is insensitive to the failure of a single node. So a perfect example of this is Bitcoin, for example. So Bitcoin has had zero downtime because of the idea that it's partition tolerant, which means that any node can go down without the whole network going down because it's a decentralized network, okay? And then the data is always available because you can always find a willing node that's able to like give us data about the records, basically. So when we talk about, we have another case where the data is always consistent and insensitive to network partitioning, but then some data is not available during a network failure. That's availability. So an example of this would be where we have like multiple data feeds basically, and we update each data feed. Like for example, we have a transaction on node one and we have a transaction on node two. So we're going to wait before releasing data to the public, and we're going to wait until we have verified both transactions and both nodes have reached a consensus before we make that data available to the public. So basically what that means is that there are going to be times during that verification when the network is going to be down, but we're always going to have consistent data and we're going to be insensitive to a node failing basically. And there's also the case where we're consistently available and we're always available, yeah. But then it's impossible to partition the network, which means it's impossible for a single node to go down because each node is doing like a specific function basically and cannot go down during the network process. So examples of distributed ledger technologies, blockchain is a very good example of this. Blockchain allows us to store multiple blocks and records of data across multiple nodes with partition tolerance and consistency. So examples of blockchains, we have Bitcoin, Ethereum, Tron, that's the Tron network. Another example of this is Hashgraph. Hashgraph is similar to blockchain, but it's not really necessary to store all records of transaction. Rather, each transaction is verified amongst nodes, basically through the gossip protocol, rather. So verification happens between nodes and it happens rather quickly because like there's no need to reach consensus in the general pool, like it's done node to node. Okay. Then we have directed acyclic graphs or DAGs. Those make it verified data through the data structure basically. So transactions are verified based on preceding transactions with like multiple algorithms basically. An example of this is the next token, the IOTA Tango and the Byte Ball. Okay. Um we can now view blockchain as a DLT, basically. So we're going to view blockchain in the light of storing data across multiple nodes in a way that is fault tolerant and is always consistent, basically. A blockchain is a specific form or subset of distributed ledger technologies, which constructs a chronological chain of blocks, hence the name blockchain. A blockchain is a read and append only storage methodology. This means that blocks can only be created and read in the blockchain ledger. Blocks in a blockchain cannot be updated or deleted. Blocks can only be appended to the end of a blockchain. There is no access control in a blockchain as it's open for both read and write operations. So what this basically means in a blockchain is like a data structure where we have preceding blocks, okay? So each block is built upon another block. So we'll talk about the block structure later in the program, but each block has like a link to a previous block's hash. So we can verify the block's veracity by like comparing it with previous blocks. So basically, we can trace the history of the whole blockchain from the current block to like the genesis block because we have like a link to each previous block's hash. Then a blockchain is a read and append only storage methodology. What that means is that we do not have the capacity to like change previous transactions because we have already like hashed them and we've already like confirmed them basically. And we have more blocks built on top of those already existing blocks. So it's actually impossible to change the block structure because that would affect the hash, which would basically render the whole block invalid rather. So there's no access control in a public blockchain. What this means is that is a permissionless scheme, so anybody can contribute to a blockchain network. Anybody can join a blockchain network. Anybody can like send transactions in a blockchain network. It's a trustless society, so there are protocols made in place to like verify transactions. Okay, so we're going to talk about nodes now. Okay, so depending on the type of network we have, there are usually two types of nodes. There are nodes that will verify transactions, and there are nodes that will like publish transactions and like view transactions basically. So we have like verification nodes and we have like client nodes basically. Not all, some blockchains and networks allow us to like have, so for single nodes to have like double functions basically. And an example of a network that has two types of nodes is Bitcoin, for example. So we have mining nodes and we have client nodes basically. So mining nodes are those nodes that verify transactions basically. So they put together transactions and they create blocks. They hash the transactions, they verify the accuracy, they make sure that you're not sending money you don't have, and then they hash them together and like put them on top of the existing block. So the method of consensus in a Bitcoin network is proof of work basically. What that means is that they perform like complex mathematical computations on the block's hash to like and to reach like a desired difficulty and to generate a required nonce. Okay, so when they do that, that block is now considered valid and is now added to the blockchain ledger. Another example of a system that has verification and mining nodes is Ethereum, although they will soon change to a proof of stake. But the idea is that we have a single miner basically which pulls together transactions and verifies their accuracy, and then he combines them together into a block, performs another computation, and then adds them to the block. Because these computations are like highly energy, they consume a lot of energy rather. So the miners get rewarded with like the native cryptocurrency of that network. An example would be Ethereum. So if you mine an Ethereum block, you get an Ethereum reward. Okay, so that's a compensation for the effort spent by the miner in verifying accounts and transactions, and in also solving the complex mathematical problem related with like solving creating a block. So nodes are clients and peers on a blockchain network, and depending on the protocol, perform different functions: mining, verification, record reading, and the likes. Okay. So now we talk about blocks more in depth. So blocks are basically like if blocks are the data storage, the data format that data is stored in a blockchain basically. So blocks are like records in a database, in a blockchain rather. So each block holds transaction records for like multiple transactions, hold like block information, timestamp basically, so we can identify transactions. So depending on the network, each block is going to have a different structure, but like there's a general format basically built off like the block Bitcoin structure basically because of it was the earliest like attempt at making a usable blockchain. So if we consider a blockchain as a data structure, then the blocks are aggregated sets of data. What that basically means is if we consider the blockchain as a record of data, then the blocks are like organized sets of that data that are stored in the blockchain and are used for the formation of the blockchain. So each block rather has a block size, which is the number of transactions within that block, a block header which contains metadata about the block, a transaction counter which like gives the number of transactions in that block, and like the list of transactions basically that were verified. So when a user creates a transaction, what happens is that the user node publishes that transaction to the general miner pool. So miners randomly select transactions to verify at once based on the gas price too. So gas price in an Ethereum node helps miners to consider particular transactions to verify at once. So after verification, after verification, the transactions get put together in a list basically and put in the transactions box. Okay. So then we also have a transaction counter, which is like the number of transactions that were put together. Then the miner goes ahead to like perform calculations basically and try to find the roots basically and the answer to the mathematical question that allows them to create new blocks. Okay. So this is a deeper look at the block header. We have the version, the network version or the network ID. So that's like an identification of the network basically. So multiple networks could have like multiple nodes, but how do we identify which one is a Bitcoin network and an Ethereum network or an Ethereum node or Bitcoin node or an Ethereum transaction or Bitcoin transaction? So this is where the version comes in place. So each network has a unique version that allows it to be uniquely identified. Okay. Then we have the previous block hash, which is very important because it means that each block is dependent on the previous block, and therefore it means the whole blockchain is deterministic. What that means is that if we go back in time, we're going to reach the same state as we are currently because each block leads to the next state and there's no like change in variables basically. You have the Merkle root, which is like the hash of the whole blockchain. So the Merkle root serves as like a storage for the whole blockchain and helps us to verify transactions going back in time. Timestamp is simply the time of the block when the block was created. So it increments in a few seconds in UTC format. And we have the difficulty target. This is specific to Bitcoin and to proof of work miners, basically. So blockchain networks that use proof of work as their consensus mechanism make use of difficulty target. The difficulty target in Bitcoin determines the number of zeros that should come in front of the hash of the block, basically. So that would basically going in depth into that basically means that the miners are going to hash all the transactions together with the nonce. The nonce is a random value, a dummy value basically, that when hashed together with the transactions creates a hash that meets the difficulty target basically. So in Bitcoin, that would be a number of zeros in the front. Each one has a different difficulty setting. So that's the idea behind the difficulty target. And this is the metadata that is contained in the block header basically. So do we have questions? Damola?
Yes, I'm here with you, Toby. Thank you very much for the presentation. So we have some questions here. Someone said, please share. Okay, Raphael said, please share light on mining rigs and mining pools and Merkle 3. So,
Okay,
yeah,
you're going ahead.
you want to
No,
take
you were
that?
saying something. I didn't get it. What were you saying
Yes.
again?
Okay, so I said someone asked to share light on mining rigs, mining pools, and Merkle 3.
Okay. So a Merkle tree, let's start from there. A Merkle tree is a data structure basically that allows us to verify identities basically on elements based on like their hashes. So we can go from the roots back to each previous transaction and verify that that transaction actually happened by like verifying each stage of the process. So like a Merkle tree is like a tree, a data structure basically of hashes. So we can use it to verify transactions. Mining pools, if I got that correctly, mining pools are groups of nodes basically that have decided to contribute their computational power as a single group to solve questions together basically. So the mining process is split across multiple computers, and each computer like solves a part of the mathematical problem basically and finally contributes that to the whole solution. So the idea is that we use like smaller computers to perform the bigger calculations basically, and so each person in the mining pool gets a reward from that mining reward basically. Okay.
Okay. Oh, okay. So we have another question. What are forks, children blocks, and uncle blocks?
Okay. So forks basically, there are hard forks and there are soft forks. Forks happen when there are like changes in the blockchain network and its software. An example of that is the Bitcoin Bitcash fork. So basically there was a change in the protocol. So some people went to adopt a new protocol. So that's where the fork came in. So in a soft fork, the new fork's data is compatible with the old fork's data. In a hard fork, that's not compatible. An example of a hard fork was the Ethereum Classic fork. Okay, so that happened during the DAO crisis, and we saw that they created like two separate forms of Ethereum basically. So that's what forking basically means when the protocol takes two different parts. Okay, so if somebody changes the version or somebody decides that they want to change the code base, so they fork it basically.
Okay, so we have uncle blocks and
Okay.
yeah,
Um,
and children blocks.
Okay, children blocks are the result of like mining basically. So children blocks are like okay, if I mine a block at the moment now, any block built on top of that block that uses like my previous block function basically is a child block of that block, okay? Then uncle blocks, we have when mining takes place, okay, we have some miners don't finish on time, okay? So somebody always wins the prize, but what happens to the other miners that were like expending their computational power. Okay, what happens to them is that the system allows that block to be added to the blockchain list. Okay, so we have the uncle block also as part of the block's metadata. Okay, so the uncle blocks also get added to the blockchain's data record, but they're not used like in the actual data structure.
Okay. So okay, I think we have another question on Merkle 3, and I think that has been answered already. So Okay, so how does one qualify to be a miner?
Okay, very good question. There is no actual qualification to be a miner. Anybody, because well, assuming this is a permissionless blockchain at the moment, so there's actually no qualification to be a miner. If you can like set up your system, you can get enough resources. You can download the networks client. I'm going to assume we're talking about Ethereum here. So if you can get like for example Get, and you can like set up your computer to like have enough processing power, and you could definitely start mining. The
Okay,
problem with
so
mining, okay, the problem with
no,
mining is like
continue, please.
the resources required to like set up a mining node. Need a lot of like sometimes you need like specialized GPUs and CPUs basically to perform those mathematical computations in like time that is actually fast enough to compete with the general mining pool. You could also join in like a mining pool too to like contribute your resources and maybe share the bulk of the work and then maybe get a smaller reward. Okay.
Oh, yeah, okay. So Taufik Bakari asked how many zeros in Ethereum and how many in Bitcoin network.
Okay, so the difficulty changes gradually depending on the like the average computing power in the network. So the Bitcoin difficulty can change from like maybe 5 zeros to 2 zeros to 3 zeros depending on network frequency and like the general computational power. So it's variable. Same thing for the Ethereum network rather.
Okay, so thank you very much, Toby. So I think another question we have here is, okay, what is the meaning of the longest chain in a blockchain?
So the idea is that stems from like the uncle block principle.
Uncle Block
So
say,
yeah. So when miners basically are mining, okay, so only the fastest miner gets rewarded. That's the first person that comes up with a hash that meets the requirements of the network. So when that miner gets rewarded, what happens to the other miners is that their rewards get like they have also created like a valid blockchain list because they also created like a result that was valid, but but they were not quick enough to do that, so that block gets added like as an uncle block, but they don't really get rewarded. Okay. So that's why we have like the longest chain because each miner like created another chain of the blockchain, but only the longest chain is considered the most valid.
okay, thank you very much for that, Toby. Um, since blockchain works in a building, okay, Akim Omosonya asked, since blockchain works in a build and append format, how do we maintain in the future since we can make an update after deployment?
Okay. I think I see two questions there. There's one about like data
Yeah,
storage and like storing records, multiple records for a long amount of time. So for that, they are still developing protocols that could help with that. But something that is looking really promising about that is sharding. So in the traditional sense is like when we split a database into like smaller subsets of records or columns. So like we can use smaller storage devices to store it basically. So that's sharding. So sharding applied to blockchain would be that we could maybe store a subset of the records that we could use for verification purposes. So not every node would need to have like all the transactions in the blockchain. About upgrading code, I'm assuming that relates to Ethereum.
Ethereum,
Um,
yeah.
okay, that falls under like smart contract upgradability, basically. So in the traditional sense, no, you cannot update your code because like that's definite in the blockchain. That's part of the deterministic nature of the blockchain. That's part of the immutable nature of the blockchain. So no, you cannot change your code if you're deployed to a particular contract. What you can, however, do is design your code base in such a way that like you create like a constant contract that like users interact with, which we would call like a proxy contract. So basically, users interact with that proxy contract, then we can have like a backend contract that you delegate calls to. So each one has this opcode we call delegate call basically. So you can delegate like calls and function calls basically to your backend contract while remaining in the scope of your proxy contract. So you will still be able to like access all your wallets and tokens through your proxy contract. So you could easily change your backend contract. So that's the idea of smart contract upgradability.
Yeah, so additional to that, we also have okay, I think we have like two different types of upgradability in smart contract now. We have
Okay.
Diamond standard in addition to what we just said. So it's another way of upgrading your contract after being deployed. So magic visual, I think the answer to the previous question should answer your question. You said, I thought in the earlier class it was said that anything deployed on the blockchain cannot be altered. Where is the block? Where is the Bitcoin, Bitcash, and Ethereum Classic?
Okay, so we're not altering the blockchain, we're changing the
Yeah.
protocol basically. So we're creating like a new version. Okay.
Is that okay? I thought
No,
you
I
wanted to
thought you were
say.
saying something.
No, no, no. Please continue.
Okay, so we're basically like changing the code base, or sometimes what happened, okay, for example, what happened in the Ethereum Classic fork was basically we weren't even changing the code base. What happened was there was a big hack and they went to reverse the hack. And some people felt that that was against the idea of blockchain, like you shouldn't be able to reverse things, you shouldn't be able to go back in the past and change. So basically, what happened was that some people forked the blockchain and created like another longer blockchain like link, basically. So there were two different chains, basically, but each one was running the same protocol. Okay. So sometimes that's what happens in forks. Basically, some people want to go back and like change stuff, but we're not. So that's where they violate the idea of immutability, and that's why these chains are not always like compatible with each other. So the idea is if we've had this network for like 5 years, nothing can change in that network basically, unless somebody forks it, and we wouldn't be using that fork to verify.
Thank you so much, Toby. So I think the last question we have here is what had system spec necessary to mine a coin?
That's dependent on how you choose to approach mining. Okay, so your average like laptop, like 8 GB RAM, is not going to like actually be able to profitably mine for you because of, first of all, you're competing with like mega computers in China. Okay, so you have to consider that. So if you decide to join a mining pool, you're only going to get rewarded based on the amount of computational power you contributed. So compared to like quantum computers, you didn't really like contribute a lot of power. So it wouldn't actually be profitable for you to leave the laptop running for like 24 hours a day without being able to use it, and then only get like maybe 2, 3 ether in a month, something like that. Sorry, that's even like an overstatement actually.
Okay. So I think that's the last question we have here. Thank you so much, Toby. We had a great presentation from you. Thank you so much. It was well explained and detailed, and yes, it was awesome. So, guys, concerning the slides, it will be shared, and yes, the video is on YouTube. You can always go back to it and watch again. So I think that's all from my hand here.
Okay.
Or do we still have anybody or any question or contribution? Okay, I think someone just dropped a question. How is nonce generated?
Okay, very good. So that's the idea of
Yeah.
proof of work. There's no actual way to predict what the hash of a value is going to be. So each mining node is going to have to randomly try random values and hash each of them and like check the value. So it's really expensive computationally wise and mathematically wise, basically to like check like random values basically. So it's randomly
Oh,
generated actually. There's no actual procedure to generating it. It's just like a random number. You check whether it works, and if it doesn't work, you try another.
yeah. Thank you. That answers it. So is there okay, there is a possibility of reversibility. Well, okay, that is from Magic Visual. Yes, it depends on how um it depends on the situation. Let me say that. I mean, in case of the Ethereum Classic, I mean the situation it was just like I think it was a vote from people to either take the hard fork or to reverse the transaction that was made, the hack that was made. So it depends on the community and the network itself. Okay, so moving on. Yes, John, the slides will be shared. And yes, thank you, Toby. Okay. So someone asked what is crypto vesting?
Crypto vesting, the idea of investing in crypto, DeFi.
No, no, not investing, vesting.
Okay, I'll take that to mean like staking. Okay, and maybe yield farming.
Yeah,
Okay, so
yeah.
that's the idea of like tying down your crypto basically. Just think of it like compound interest. Okay, so you're
Mm-hmm.
tying down your crypto basically for future. So the people that you gave this, you staked with basically have the right to like trade with that Bitcoin basically and produce whatever they want. What you get at the end of the staking period is like an interest of your money basically. So just a typical compound interest scenario, but just a decentralized version.
Okay, thank you very much for that. So, Kolawole Ogunfowo asks, aside Remix, is there any other ID that is good for Solidity? Of course, yes, you can use VS Code. We have VS Code. Remix is an online ID for Solidity. So, okay, I'm looking if okay, I think someone just asked, what are majorly the cause of having a fork version of a smart contract like Bitcoin Cash?
Okay. Depending on the nature of the fork, they're like soft and hard forks.
Exactly.
So the results would be either the new fork is incompatible with the old fork. But the whole idea is we've basically created another network. Okay. So you can't basically communicate with each other basically. So the old network can't communicate with the new network. New transactions happen on the new network. They don't always happen on the old network. So we've created like basically two separate networks. Okay. So sometimes when this happens, we have like the double spend problem if you're not careful about like protecting both networks from the double spend problem, because the two blocks would usually be like relatable and like interchangeable, okay? But like so there are protocols that defined when making forks basically to prevent the double spend problem.
All right, thank you so much. Chidi, you said you had a question before you didn't answer it. Please, can you ask the question again? Probably I missed it. I'm sorry about that. So Tess is asking, is decentralization the core of Web3? Yes, of course. Decentralization is one of the core concepts of Web3. Um, can you show an example of a block header? Okay, can you show an example of block header? That's from Chidi.
Okay, I don't have Get running at the moment, but I'll do like a tutorial video on how you can set up Get to like run a private blockchain on a system. In that case, what we'd have is like the block hash and like a list of transactions basically. So it would just look like a JSON file basically, like a JSON format.
Okay, thank you very much. Raphael Tanko is asking, will it be ideal we study on cryptography?
Okay, so it's good to know about cryptographic primitives, basically like asymmetric and symmetric key and like encryption. So the idea is like blockchain employs a lot of cryptography. So we have like asymmetric pairing and encryption, and the idea of like public and private keys for your wallet. You have the idea of like symmetric encryption for like verifying transactions too. So that's the whole idea. So blockchain is actually built on top of cryptography. So it'd be nice to have a background in it, but it's not like necessary to go too deep. Just the basics are
So the
okay.
yeah, so why hiring network interoperable?
I didn't get that,
Okay, you're
sorry.
talking interoperability in networks.
Okay, if you want to take that, you can take that.
No, you can take it if you want to.
Interoperability,
Yes, of networks.
that's the idea that they can like we can share between
Work
networks, right?
together. Yeah.
Yeah. Okay, so like we have like decentralized exchanges that can help with that. So maybe we can have like Polygon, for example, helps Ethereum basically as like for optimization purposes. So like we can perform like very heavy computations on like the Polygon network and then like move those to the Ethereum network. So if I understood your question correctly, that's how like networks could help each other.
Yeah. Thank you. That's the last question we have here. Okay. Are we waiting for more questions or
No, I think we can call it a wrap. It's been like an hour.
all right, so we have 10 minutes to go, guys. So we are waiting for your questions to that was amazing, Toby. Thank you very much.
Thank you. Thank you so much.
Okay, guys, so we'll be taking some questions from the Discord. I'm trying to look for questions on the Discord. Okay, so someone asked for your thoughts on about Cardano's blockchain, Toby. So Clinton is asking about your thoughts on Cardano's blockchain.
Network cut me off there.
Okay, so someone is asking about your thoughts on Cardano's blockchain.
Okay, so the idea at the moment is like blockchain is really limited scalability wise. So it like takes a lot of time for transactions to be verified. Example would be Bitcoin, for example. So it takes like 10 minutes for a block to be created. Okay. So if we can get like networks basically, Cardano promises to do that, okay, that can verify transactions faster and like make sure they're efficient, okay. That would be great. It will like open up the blockchain space to like better and more wider use cases, okay. So like an example of like a protocol that's being developed, okay, to help like scalability is like zero knowledge proofs, okay. So we're designing like mathematical inductions basically where we can prove something happened without like having to transfer all the data that made that thing happen. So we can verify and prove data without sending large amounts of data. So I believe like Cardano, if Cardano is able to like promise on what they like deliver on what they promised rather, it would be great like for scalability wise. So you could use that in terms of the other network basically to partner with other networks to like help speed up stuff.
All right, thank you very much for that, Toby. I'm still trying to look for the other questions on the Discord. Okay, I don't think we have any more questions.
Okay.
Yes, I don't think I have
You
any
go,
more questions. Okay,
okay.
so I think a question just came in. How had these other blockchain created? I mean, without Solidity and Rust, are there more?
Okay, so you could actually like implement like a blockchain-based data structure with like any language of your choice. Rust is used for speed, Solidity is used for programming smart contracts. Like that's a choice, okay? So the idea is just to like create a network that verifies, okay, and that allows users to like create transactions. That's the whole idea with blockchain. So you could implement that data structure with any language of your choice. You just have to consider scalability and like security wise. So the
Yeah.
idea of like when you're creating like a blockchain, you have to consider like how are you going to verify transactions? How are you going to like hash those functions together, cryptographic angles of that. So it's like a very deep topic, but it's actually possible to create your own. There are like lots of other networks and like blockchain networks apart from like Bitcoin and Ethereum. Okay.
All right, someone is asking for your full name on LinkedIn.
Ah, good. Um, full name is Emmanuel Kashi. Okay, that's me on
Okay,
LinkedIn.
okay, can you spell that? I get the man now.
Okay,
K-A-C-Y-T-C-H-Y.
Katchy. No, rather Katchy.
Okay. All
Yeah.
right, thank you. So I think that is all we have for today.
Okay.
So I guess we'll be rounding up now. Thank you everyone for joining. Thank you so much. I had a great time and a great presentation from Toby. So thank you
Thank
guys.
you. Okay.